All right, so here we are. Just want to open up one thing and we'll be ready. Okay. So today's the 19th. 2/19. All right, very good. All right, so last time we were looking at elasticity, the price elasticity of demand in particular, and what we were trying to estimate here is how sensitive people are to changes in prices. In other words, when prices change, we know that the quantity demanded of a good changes. The question is how much? And so that's what the elasticity is attempting to measure. And so we'll see that this is a very important measure in a lot of applications. So it may seem like a very abstract idea at first, but we'll see that we can get a lot of use out of it as well. So if you recall, we were talking about this example where a computer company, let's say it's Apple, raises their prices by 10%. And as a result, there's a significant drop off in the quantity demanded. And that's because, of course, that 10% increase in price represents $200, which is quite a bit of money. And so a lot of people will think twice about buying that new computer, even though the price only went up 10%. On the other hand, if Starbucks does the same thing, they take one of their $2 coffees and raise the price by 10%. That only represents a 20-cent increase, and people may not even notice that. All right, maybe a few people will stop buying the coffee or buy less of it, but for the most part, it won't have much of an impact on the quantity demanded of Starbucks. So what that means is that there's a different level of sensitivity of consumers to the prices of these two different goods. And so the elasticity measure will make it possible to capture this sensitivity and compare the two goods side by side to determine which is the most elastic and which is the least elastic. Okay, so we noted here last time that there's actually three different kinds of elasticity that we want to look at in this chapter. Although there are more, these are probably the three most important ones. And the one we've been looking at up to this point is the price elasticity of demand. But later on today, we'll also be looking at the income elasticity of demand. And then, of course, the cross elasticity of demand. These are not quite as complicated, but they're awfully important too. All right, so in general, any elasticity is defined in the following way. We have a percentage change in the quantity demanded in the numerator. In the denominator, in this example, we have the percentage change in price. For the other elasticities, we'll have something different in the denominator. But we always have the percentage change in quantity demanded in the numerator. The denominator in this case, because it's the price elasticity of demand, is the price of the good. So now, oh, by the way, within this formula, you'll see this is simply shorthand notation for percentage change. You recall that this triangle is actually the Greek letter delta. And you know from experience, this always represents a change of some kind. So when you combine the two, and this is a common practice in most books, this becomes percentage change. Okay, so that's what that's meant to represent. Let me just quickly put that in here. And just delta by itself, you can think of that as absolute change. Okay, so then we formally defined it with a formula. So delta Q will represent Q2 minus Q1 based on the assumption that we've moved across a demand curve from, let's say, point 1, where we have P1 and Q1, down to, let's say, point 2, where we have the second and the first, the second price, the second quantity. And so the difference in the Qs is the difference between these two values. So, you know, in other words, this is the absolute change in Q. It's not the percentage change, it's the absolute change. How much did the quantity change when the price changed? That's what we're trying to capture. Right? We'll just make this a little neater. Then we can do the same thing for the price. If there's been a change in quantity, it must be in response to a change in the price. And so here you can see once again, given that we're moving along the same demand curve from, let's say, point 1 to point 2, here's P1 and Q1, and here's P2 and Q2. So now what we're trying to capture is this difference right here, the difference between the prices. So this is the absolute change in the price. And what we're essentially trying to find out is how much of a response was there in the change in quantity demanded to the change in the price that we see. Now, I do want to mention, though, that in order to have a percentage change, these are absolute changes, as I mentioned. So, for example, delta Q2, or delta Q is Q2 minus Q1. The percentage change in Q, though, means we take this expression and we divide by Q1. And we do the same thing for P. And then here with the percentage change, all we have to do is divide that by the original price. So if you notice the pattern here, the changes in the numerator, the original value is always in the denominator. And so in the absolute change, we keep the original units. Quantity would be units of the good, P would be dollars, but now down here, these are simply percentages. And then finally, once we combine these, the elasticity is the ratio of the percentage change in Q to the percentage change in P. All elasticities are calculated as the ratio of percentage changes. Now, we did mention, though, that there is an issue here that we need to be aware of, that unfortunately, one of the real problems with this measure is that the way it's defined, the price elasticity of demand will be different if we go from 1 to 2 than if we go from 2 to 1. Okay, and that's extremely awkward. And part of the reason for that, just as a little side note here, this is one of the really quirky things about the supply and demand curves. I mean, the way we think about it is with a normal XY coordinate system, Y goes here and X goes here. And we know that Y is a function of X, fine. But if you look at the price and quantity setup here, these are actually reversed because it's pretty much understood that Q is a function of P. It's not the other way around. And yet, look what happened. Based on that logic, X would be P and Y would be Q. And yet, look at where they are. They seem to have been reversed from what we're used to seeing in the XY coordinate system. Now, why did this happen? How come we don't have Q on the vertical axis and P on the horizontal axis? And by the way, this is why the elasticity is different at 2 different points in the curve. In the 19th century, when microeconomics was still in its infancy, there's a very, very famous economist named Alfred Marshall. And he was like the most famous economist of his time. And so it was Marshall's idea to put price on the vertical axis and quantity on the horizontal axis. I don't remember the exact logic he used, but this is one of the unfortunate consequences, is that the elasticity measure will be different if we move up and down the curve. So what do we do about it? Oh, well, as a compromise, what we're going to do is we're going to calculate the average elasticity across these 2 points rather than the actual elasticity at each point. And so we have this compromise formula, I guess you could call it, which is sometimes referred to as arc. We're not going to use that terminology here, but sometimes this is called arc elasticity of demand because we're essentially calculating an average over 2 points. Actually, I left out a word here. It's arc price elasticity of demand. The one where we have the actual percentage changes without using an average is sometimes called the point price elasticity of demand. And that's just for your knowledge. I'm not going to test you on that, but the original measure is called the point price elasticity of demand. This one that we're going to use instead is called the arc price elasticity of demand because we're averaging out over 2 points. You can see it's a little bit messier down here. The Q has been replaced by an average. And the same thing with the price. And this eliminates the problem that, and in fact, so when we do it this way, it'll be the same measure no matter which direction we go in. And that's why it's often used instead of the point price elasticity of demand. It doesn't cause, if this difference between the 2 points is small, these two measures will give us a very similar answer anyway. So it's not that big of a deal, but if we're moving across a long distance on this demand curve, then the differences could be fairly noticeable. Okay, but it's understood here that we'll be sticking with the arc price elasticity of demand, again, to avoid that problem that it'll be different depending on where we start and where we finish. All right, so we took our pizza example from chapter 4 and started doing some calculations. And so let's just say that we start at a price of 8. This will be P1. And we're going to cut the price of the pizza. For whatever reason, we decided that we might be able to stimulate sales by cutting the price. And we'd like to know what is the price elasticity of demand across these 2 points. Okay, so what we're basically doing here is we're moving from the first point was 8 and 6, and now we're at 6 and 7. So we'll think of this as point 1, this is point 2. So we know that like I said, P1 is 8, P2 is 6, Q1 is 6, and Q2 is 7. And we can now plug these numbers in and come up with a price elasticity of demand. All right. Now, I mentioned last time too that I think our best bet with these calculations is to do it in stages rather than try to plug it all in at once, because you're bound to run into problems. Okay, so in other words, if you look at the formula, let's put this on a separate slide here. All right, so let me repeat this information one more time. So we're going to use the arc elasticity formula, the averages. So we start out with Q2 minus Q1 over the average of the two. See, it's getting unwieldy already. So why don't we try this? First of all, let's rewrite it. As the product of this term times the inverse P2 plus P1 over 2 divided by P2 minus P1. Okay, so algebraically, these are equal to each other. And now what we could probably just do is find or solve for each one individually and then multiply them together. Okay, so if we do that, let's start with this first one. I'm going to wind up with 7 minus 6 over 7 plus 6 over 2. Okay, and that's equal to, that's 1 over 6.5, which is approximately equal to about 0.1538. Now this one, the second one, is going to be 6 plus 8 over 2, all divided by 6 minus 8. So you're going to have 7 over negative 2, which is equal to negative 3.5. And now I have to multiply them together. Let's see, I'll put these up here. And let's see what that gives us. It's negative 0.5383. Okay, so that wasn't so bad. That wasn't so painful. So now you don't have to do it this way. You can plug in the numbers yourself and do it algebraically, but I kind of like the idea of doing it in stages, because then I think that helps reduce the risk of errors. All right, I don't know if you agree with me. That's okay. You can do it however you like, but I kind of like this approach. Okay, looks like we're all here. All right, now the question is, what does this mean? And by the way, if you notice, one of these two ratios has to be negative, okay? Because you know that Q and P are moving in opposite directions. The slope of the demand curve is negative. So if the term on the left is positive, the one on the right has to be negative, and vice versa. So what do we do about that? Now, as I mentioned the other day, for certain types of measures where it's understood that the result is negative, we often see that we just use absolute value, because a lot of people find negative numbers to be very confusing, and they can be very clumsy to work with. So by convention, what we'll do, at least in this case, is we'll just ignore the sign. It's understood that it's a negative number. So if you see it written down, let's say if you're reading an article in the newspaper about elasticities for some reason, and you'll see a chart of them listed, you won't see any negative numbers. They'll just have a list of the positives, because again, we just find it a nuisance to deal with the negative numbers. This won't be true with the other elasticities, by the way, because in those cases, the sign is very important. But here, because it's always a negative number, we can feel free to only use the absolute value. That being the case, we can focus all of our attention on the magnitude. In other words, where does this stand compared to 0 or 1? Those are the two numbers that we want to focus on. So now let's take a look and see. Now, these are all the calculations. I've done them again, of course. 0.538, what does that mean? Well, first of all, how do we interpret this? For each 1% reduction in the price of the pizza, the quantity demanded will go up 0.538%.
Accidentally used your credit card yesterday. Food.
Hey girl, you're not muted.
Got it. Uh-oh. Any second now. I hope we were not about to hear somebody's credit card number. So I muted it just in the nick of time, I think. So anyway, and then the opposite is true. If there's a 1% cut in the price, for every 1% increase in the price, oh, actually, this is the decrease. If there's an increase in the price, then the quantity demanded should drop by 0.538%. So that means that, let's say the actual price reduction, let's say we do put the pizza on sale. Let's say if the actual price reduction is 10%. That means that the increase in the price, the quantity demanded, can be easily calculated. You just multiply it by 10. Okay. So it's a very helpful measure to have. And it's great to have this information as the owner of a business, because you need to know to survive, you have to have some idea of what is the optimal price to charge for your product. Now, a small business like a pizzeria may not have the wherewithal to do extensive market research about the elasticity of demand for pizza, but at the very least, they know from experience how much revenue they took in when they charged different prices. In other words, they may have experimented in the past and had price sales, and maybe they've increased the price, and they want to see how the customers react. So they have to have some idea of what would be the best price to charge. And once they find that, they'll charge that price. They don't want to keep changing the price. That's not good for business either, because people like consistency. And so, but for a larger company, for a corporation that has a marketing research team, they probably will go out and use a lot of research to determine the elasticity of demand for their products and use that information to come up with the perfect price that maximizes their profits. Okay, so this is hugely helpful to any business enterprise to have this information. We're going to see why in a few minutes, or how this helps us come up with the best price. Now, here's the classification. All the elasticities have a classification, so you can tell what the numbers actually mean. So given that we're ignoring the sign, for the price elasticity of demand, the three numbers that matter are, is this number less than 1? Is it equal to 1? Or is it greater than 1? This will tell us a lot of information about the demand for this product. So for the pizza case that we just calculated, we came up with 0.538, which puts us in this category. Okay, 0.538 is clearly less than 1. So for the pizza, the demand is said to be inelastic. For one exactly is a very rare case. It is referred to as unit elastic because unit simply means 1. And then above 1 means the demand is elastic. And I mentioned this before, inelastic means not very sensitive or low sensitivity. Elastic means high sensitivity. So if you recall from before, when we're looking at the Starbucks case, Starbucks demand would have been very inelastic. People didn't really care very much if the price went up 10%. They only bought the reduction in quantity demanded was very minimal. And here, for the computer example we had, it was very elastic. People were very upset by the 10% price increase. And so even though we didn't actually calculate the sensitivities, or we could have, but we didn't, it's pretty clear that with Starbucks, the demand is inelastic, whereas with the computers, the demand was very elastic. All right, so now this will help us as a business determine what to do about our price. If it's not already the optimal price, we need to know whether we should raise it or lower it. If we make the wrong decision, it could cost us a lot of money, and we could even go out of business. So this is a huge deal. So this is what I was building up to. Elasticity and total revenue. Now, total revenue simply means how much money am I bringing in from my product? We're going to define that formally as the price of the good times the quantity. It's very simple. So if I sell 100 units, let's say, or like with the pizza, let's go back and revisit this for a second. When I reduce the price, all right, let's take this case. In this example we've been working on, when the price was 8, then people bought 6 million pizzas. So we can use this information to calculate their total revenue. So the price was 8. The quantity was 6 million, that is. So the total revenue in that case, we'll call it TR1, is P1 times Q1, which is 8 times 6 million, which means that they're bringing in $48 million in revenues. Now, we don't know how much their costs are, so we can't be sure if they're making money, but we do know that they're bringing in $48 million in revenues. That's important because this is the part that we don't really have any control over. We have to, our revenues depend on the demand from the public. The costs of production depend to a certain degree on how we choose to make the pizza. But this is something that we don't really control. All we can do is hope that if we charge the right price, we'll get more money coming in. Now, it turns out there's a very specific relationship between elasticity and revenue. Okay, so here's how it works. And we're going to prove this with some examples. All right, here we go. When the demand is inelastic, raising the price will raise our revenues, and vice versa, which means the opposite. When the demand is unit elastic, no matter what price we charge, we're going to have the same total revenue. And that's the bizarre case. Okay, so don't worry, we'll summarize this in a table so you can see very quickly and easily how this works. Which means that when the demand is elastic, it works in the opposite direction from when the demand is inelastic. Of course it does, it has to. All right, so we'll add that to our list. When the demand is elastic, an increase in the price will actually lower our revenues and vice versa. All right, it looks like I just noticed I do have a nice little chart here. I don't know about you, but I find that having a chart is hugely helpful. It's so easy to see what's going on at a glance, as opposed, just to reading a bunch of sentences, which may contain the same information, but there's something about a chart that makes it so much easier to visualize what's going on. All right, so let's take a look at this chart. And it's just the same information, but I think it's organized in such a way that it'll be much easier to follow what's going on. All right, so here we go. So with an inelastic demand, if you raise the price, you'll have more revenues. If you cut the price, you'll have less revenue. So the price and the revenues are going in the same direction. Here's the strange unit elastic case. That is the case where no matter what price we charge, we'll get the same total revenues. And then with the elastic case, raising the price would be a terrible mistake because you'll drive away a lot of customers and your total revenue will drop. Whereas down here, it's the other way around. This is exactly when you want to cut the price. You want to put things on sale when their elasticity is high because people will buy a lot more of the product. And in fact, you can start to get a sense of this by going to any supermarket. The products that tend to be put on sale on a regular basis, most likely they have a relatively high elasticity of demand. The prices that never change are more likely to be the ones that are inelastic. So people don't want any changes there, or at least, or the price may even go up. But yes, the things that tend to go on sale are the ones which are more likely to have a relatively high elasticity. Because the store's experimenting. They're trying different prices. They're trying to see what would be the price at which the revenues are maximized. That's all they want to know. And if you look at all the prices in any retail outlet, any place, the prices were not randomly chosen. They were chosen after experience with seeing how people react to different prices. So with the pizza example, here's what I've done. I put together a chart in which I'm showing the prices and quantities and the total revenues as well. And if you look at it carefully, you'll see that our revenues are maximized right here. All right, any other price would be a mistake. Because our revenues are maximized here, that means ideally we'd like to charge $10 for our slices or pizzas and sell 5 million of them. And it's understood these are millions. So anyway, so I've got a bunch of diagrams here. We don't necessarily need to go through all of these right now. It was just the point of it was to show you in terms of geometry, why this is happening. For example, if we started at A and we go down to B, let's just quickly run through one example here. From point A, we have a price of 16. Let's go back to the chart. Point A will be this one. Okay. And point B will be $14. And you can see that if we started at A price cut is raising our revenues. All right. A price cut is raising our revenues. And so that implies that the demand must be elastic in this region. So what I'm going to show you here, let me just show you add another diagram here real fast. Before we go any further, it turns out, and again, this is a consequence of the way Alfred Marshall chose to set up the demand curve. The elasticity or price elasticity of demand will be different at different points along the demand curve. So in other words, it's not the same at every point. So the way it works is this. And remember, we're ignoring the sign. For a straight line demand curve, okay. Now, remember the way our curve was set up. In fact, let's go back. No, actually, we don't need that. We can go back and look at the schedule right here. When the price is 0, people are willing to buy 10 million pizzas. Okay. The price is 20. They will sell no pizzas. Now, there's a point here at $10. We're able to sell 5 million pizzas. Now, if you look at this graph very carefully, you'll see that this point is the midpoint of the demand curve. What do I mean by that? If you notice on the vertical axis, 10 is halfway between 0 and 20. And on the horizontal axis, 5 is halfway between 0 and 10. So because this is a straight line, we define this point as the midpoint. And it turns out that everywhere above this point, we discover that the elasticity is greater than 1. Down here, the elasticity is less than 1. And exactly at the midpoint, the elasticity is exactly equal to 1. Now, why does that matter? Because we've seen from that chart that when the elasticity is above 1, it makes sense to cut the price. And when the elasticity is low, it makes sense to raise the price. So therefore, from the perspective of the sellers, this is the optimum point. This is where you'll maximize your revenues. All right, so 10 and 5 is where we'd like to be to maximize our revenues. And as we saw in the chart, this is exactly correct. In fact, let me just scroll back to it for a second. I don't want to interrupt your copying, but right there, see 10 and 5 is where we have a maximum of $50. In the region where the prices are high, cutting the price is raising the revenues. Down here, raising the price is raising the revenues. This is the place that we want to be. All right, let's just color that in so you can see it. So let's go back to the graph. I know you were probably copying it. Let me just put it back. So I just want to show you numerically and graphically that this leads us to the conclusion that we would like to ideally be at a price of 10 and a quantity of 5, because that's where revenues will be maximized. Now you can prove this with geometry. I think we'll skip over that right now, but we're able to show it algebraically as well. And it turns out that the ideal spot to be producing at is right there. If the elasticity is above 1, we want to cut the price. If the elasticity is below 1, we want to raise the price. All right. So this is the relationship between price and price elasticity and total revenue. And this is why it's so important to know how this demand curve works so that you can decide what is your best price to charge for your product. Now, if you don't have all this information, you can experiment. You can, like here, we could raise the price to 11 and see what happens. Then we could lower the price to 9 and see what happens. But eventually we'll come to the conclusion that $10 is the way to go. And that's the bottom line. All right, now let us see what's next. Oh, yeah, I did have a graph in here. Oh, that's okay. Now I think we understand it better. So, but yes, I did have this chart in here too, just to remind you how this works. All right. By the way, I do want to point out too, there's a couple of special cases. If we find ourselves exactly at, oh, where is it? I lost it. If we keep moving up in this direction, the elasticity here at the, the intercept is actually infinity. And down here at this end, the price elasticity actually equals 0. Okay. All right. Those are the extreme cases, of course. One other thing I want to point out here, which is kind of an interesting, quirky little result, is that when we have a product where the price elasticity of demand is exactly 1, there's a special case that we want to consider here. If the demand curve isn't a straight line and it has this shape, this curve has a formal name. You may remember this from high school geometry. It's called a hyperbola. If this is our demand curve, then the price elasticity of demand is 1 along the entire curve. Which means that total revenue is the same at every price. And again, this is a very, very unusual case, but it can happen. But most of the time we'll have the straight line curve that we were just looking at, where the elasticity changes as we move along the curve. Okay, but just remember, this is a possible case. Think of it as an extreme case. Not like it is to be seen in practice, but possible. Now, there's a couple of other oddball cases that we want to consider as well. And again, think of them as extreme, like possible, theoretical possibilities, not likely to happen in practice, but they could happen. All right, so what could those be? This is unit elasticity. That's exactly right. This is unit elastic. This curve, we have a good that is unit elastic at every price. Exactly. All right, so let me show you 2 extreme cases, and then we'll have, this should basically finish our discussion about the price elasticity of demand. What kind of good, that's a very good question. You know what, let's see if we can find that on the internet. I can't think of any examples off the top of my head. Let's try that. Yeah, I don't know if we're going to find one that's actually. Yeah, they're making up examples. I don't know if they're. I mean, we'd have to do some research to see if there does exist such a thing. There may not be an actual product like that in the real world, but we have to allow for the possibility that it could happen. So now what we can do, though, is maybe find a chart, list of price elasticities of demand for real products, I guess, real life examples. Okay. We might be able to come up with a chart. Oh, okay, maybe. Oh, this is like, oh my. Let's see. Now this is I think this is a British website. So they're coming up, they're saying here's some cases like petrol. In England, they call it petrol instead of gas. That's how we know this is a British website. They're saying this is where we have inelastic demand. We have petrol, salt, any good produced by a monopoly, tap water, diamonds. Man, look at these. Peak rail tickets, that would be, they mean the train. Cigarettes and iPhone, really, iPhones and iPads, wow. Let's see, down here, these are the elastic ones. Why Heinz Soup? I don't know. Shell Petrol, Tesco, that's a British supermarket chain. Daily Express is a newspaper in England. Well, okay, they have Kit Kats too and Porsche. I don't know why these would have those particular elasticities, but yes, I mean, researchers have done this kind of work to try to figure out what in practice these look like. Okay. Oh, let's see. Yeah, see, this is nice, but I mean, what we wanted was some real world examples. Oh, let's see. Yeah, they're all doing a nice job of explaining it, but I don't see any actual examples. I like this page. They're doing a nice job with all these very nice real world, actual examples, and this is good. Khan Academy is very good for almost anything you want to learn more about. Look at this. Wow, that's a nice one. But anyway, I guess I'll later on I'll search and see if I can find some actual examples. The book might have some. If you look in the this chapter, there might be a chart in there somewhere that has the actual examples that you might run into. I don't think. Oh, wait a minute. Oh, look what I found. I think I stumbled onto this a long time ago and I forgot all about it. I guess I'll have to post this. Look at this. What they've done is they've actually calculated elasticities for all these goods, and you can see we have very low elasticities for salt, matches, toothpicks, airline travel in the short run, gas, coffee, fish, tobacco. The thing that these all have in common is that either the price is very low or it's something you have to have and you're not going to be that concerned about the price. Like coffee, well, it's inexpensive. Doctors, you're not going to say no to the doctor just because of the money. Unit elastic, these are the ones right in the borderline between inelastic and elastic. And elastic, these are the ones that you might think twice about buying if the price goes up too much. Oh, a life-saving drug. I'm glad you mentioned that. That's one of our extreme examples that we're about to look at. In fact, let me go right to that section right now. There's two extreme special cases that we might run into. Let's jump to the one you just asked about, this one. This would be a demand curve where the elasticity is zero along the entire curve. And so what that means is that whatever this product is, people will buy the same amount regardless of the price. And this would be the life-saving drug. And you can see why. You're not going to buy more of this drug because the price goes down because you don't need it. Let's say that this is a drug, you need a certain amount and that's it. No, more doesn't help you, less means you don't live. Okay, so if the price goes down, you will not buy more. If the price goes up, you can't buy less because then you won't be alive. So this is an example of what we call inelastic or perfectly inelastic demand. And that's because you must have this product to survive. All right, let's say you're diabetic and this is insulin and you must have it or otherwise you'll die. So you're not going to even be, this is not even a consideration. You have to have that much and that's it. It's like, or those, what are those things called that you give yourself a shot if you're allergic to peanuts or something? EpiPens, is that what they're called? Does anyone know anything about that? You've heard of those, haven't you? Well, all right, well, maybe not. If you're severely allergic to something like peanuts and you accidentally get your hands on a peanut, you can give yourself a shot that will give you time to get to the hospital before it kills you. Basically, in a nutshell, it's a substance called epinephrine, or they call it EpiPens for short. And you basically keep it with you at all times. And if you have an accident, you accidentally get yourself exposed to something you shouldn't have, it means that you'll have some time to get to the hospital before, obviously something bad happens. And so for those, there was a scandal a while back where the producer of those EpiPens suddenly decided to jack up the price like to something truly absurd. And there was such a big backlash that the company decided, maybe this isn't a good look for us. Let's just cut it back to a normal price. Because if we overcharge, people will die. That's not a good look for any corporation. All right, but then what about the other extreme case? How about this one? If the demand curve is horizontal, this is an interesting case. Here we have an infinitely elastic demand curve, or perfectly elastic demand. Now, this is another extreme case, as you can imagine. This one means that if the price, let's say this is the market price, it's $10. If the price increases even by a penny, the demand will fall to zero. In other words, if I'm a producer of this product and I try to charge $10.01 for it, I'll lose all of my business, all of it. Oh, sorry, I wrote the wrong thing here. Quantity demanded. That's how sensitive these people are to changes in the price. Even a penny means that they'll stop buying it, period. That's what we mean by that's as sensitive as it gets. Even a penny. Imagine Starbucks, you walk in there and they're charging $2.01 for the coffee, and every single person walks out of the store and refuses to buy it. That's what you're seeing here. Now, you might think that this is a very oddball case that you're never going to see in practice. We're actually going to see in a later chapter a situation where this actually can occur. So it's not as outrageous as it sounds. Okay. It is an unusual case, but it's not impossible. Okay, so this one, and by the way, if you notice, the elasticity is infinite throughout the entire curve. Whereas the vertical one, it's zero because there's no change at all. And remember too, the elasticity is defined as the percentage change in quantity due to a given change in price. In this case, the percentage change in quantity is just zero because it never changes. Therefore, this ratio is also zero. If you look at the other one, the horizontal curve, what's happening here is that given that the elasticity is defined like this, the price never changes. Oops. Okay. So therefore, look what happens here. You're going to get some percentage change divided by zero. And of course, you know that you're not allowed to divide by zero. So we call this infinite or infinity. But of course, most of the time, our demand curve will be the nice, normal, downward sloping demand curve. Now, also here, I've also included the the special case, which I forgot to mention is called the hyperbolic demand curve, that would be the one where the elasticity is 1 throughout the entire curve. And that's because it's a hyperbola, which I mentioned before. Hyperbolic is an adjective that means it's a hyperbola. And so it looks like that. Everywhere along that curve, the price elasticity is exactly 1. Now, I also want to point out that even among the downward sloping demand curves, we can have variations. For example, let me show you 2 cases. Every demand curve that's downward sloping is not the same. In other words, let's look at these 2 demand curves. They're both downward sloping, but here the elasticity, let's say that this is a highly elastic demand curve, and this one is highly inelastic. This is the steep one, is the one where even a huge price change won't cause a very large change in quantity. The flat one is the opposite. So think of this D2 as the Starbucks case, and think of this as the computer case. So just try to remember, a steep curve means that consumers are unresponsive or show little response. To price changes. And with the flat ones, consumers show a great deal of response. To price changes. Now, you can tell too, remember the vertical demand curve is the one that's 0 throughout the entire curve. This very steep one is getting close to that. The flat one is the one where the elasticity is infinite. So this flat one should have a higher elasticity because it's getting closer to that perfectly elastic case. The steep curve should be closer to 0 because it's getting very close to that vertical case. So that's how you can tell them apart. Just remember the extremes. Flat is infinitely elastic. Vertical is inelastic all throughout the curve. So these are getting closer to those extreme cases. All right, so now we have a discussion about what actually determines how elastic the demand for a product is. We also have 2 other elasticities to consider, but before we do that, I have a really nice video that I'd like us to watch that helps tie together a lot of what we've seen here today. So as usual, I will post the link in your chat room, and then let's check this out. Okay, and then we'll go over it when it's done. I think you'll like it. All right, so I'll pause the sharing and let's take a look. Gravity does more than catch errors. All right, I guess, is everyone pretty much done? Very good. It was good, wasn't it? It really is very, very helpful to see more graphical examples. And this guy, I use this guy's videos all the time. I think he does a nice job of explaining these these concepts. And all right, anyway, so let's get back to, obviously we're almost done for the day, but I just want to show you a few more things. Specifically, we want to go over, we'd like to go over some of the factors that actually determine why some products have such a different price elasticity than others. In other words, we already looked at the example of Starbucks and computers, and I think that makes intuitive sense. But we want to do a little bit more of a formal analysis of what exactly is it that causes some products to be so elastic and some to be so inelastic. Okay, so let's do that now. There's a handful of factors that really are primarily responsible for the price elasticity of demand. First of all, ultimately, what really people care about is if this product becomes more expensive, are there other substitutes we could choose in its place? Okay, now obviously for a life-saving drug, there are no substitutes, and so therefore the elasticity would be zero basically. But for most products, there are other things we could choose from. And in some cases, there's many things we could choose from. For example, Coke and Pepsi. We love those as substitutes. Clearly, if the price of Pepsi goes up, we have a lot of other options to choose from, a lot of other options. And so because of that, the demand for the elasticity of demand for Pepsi will tend to be very, very high. In other words, the minute the price of Pepsi goes up, people are likely to switch to other substitutes. Whereas a product like gasoline, let's face it, I mean, what else, if gas becomes more expensive, you have to go to work. I mean, you have to go to school. What are you supposed to do? You can't really buy less gas. I mean, sure, you can cut it back a little, but you're really kind of forced to continue buying the gas, even if the price goes up. So for something like that, the elasticity would tend to be very, very low. Now, the proportion of income, I think we made this point with the Starbucks and the computers examples. Obviously, we saw that 10% increase meant 20 cents with the Starbucks coffee, but $200 with the computer example. And so because of that, the responsiveness of people to the increase in the computer price was very, very high. The responsiveness of people to the increase in Starbucks was very, very low. So in general, the more expensive a product is, the higher will be the price elasticity of demand. All right, and that just as a rule of thumb, the more expensive something is, the more sensitive people's demand will be for that product. Then there's the time period. We have to think, in economics, we often make a distinction between what we'll call the short run and the long run, because behavior can be different in two different time frames. Like I mentioned with the gas example, in the short run, if you go to the gas station tomorrow and the price is double, you're going to be upset, but there's not a whole lot you can do about it. But in the long run, what can you do? You can buy a car that gets better gas mileage. You can move closer to school. You can move closer to your job. There are other things you can do in the long run that are not available to you in the short run. So the bottom line is the elasticity for any product tends to increase as time elapses because you have more time to find other substitutes. All right, so we're going to summarize all of these in a chart at the end here. And that too, you can buy an electric car. I forgot all about that. Yes, those are getting to be all the rage. In fact, the parking garages at some of the schools that I teach at have these I don't even know what the proper name is, where you can plug in your electric car. There's a little meter there. I guess you buy it just like like gas, but your car has to be plugged in. And charging stations, that's what they're called. So you're starting to see those pop up in parking garages everywhere because more and more people are getting electric. And I'm sure that trend will continue in the future, although I think it's going to take a while because it's a new technology and it takes time to be adapted. But down the road, you wait and see. In 10 years, a lot of people will have electric cars, and then you can say bye bye to the gas. Okay, it won't happen overnight, like when high tech products come along. Like you might recall that music used to be sold on CDs, and that pretty much disappeared when it became possible to download music from the internet. But this one will take longer. But yes, this is definitely the long-term trend towards electric. So the problem is, like right now, I'd be nervous because I don't know if I can count on there being a charging station wherever I need to go. But as that becomes less and less of a problem, more and more people will probably buy one. But anyway, oh, that too. I'm from what I understand. But the thing is, like any other new technology, in the early stages, the technology, the high tech products will be very expensive because they can only make a few because the demand is small. But as more and more people buy them, the price will start to fall as well. It's like the early desktop computers were dreadfully expensive, but as people started to buy them, yes, probably in the long run. I don't know if those cars last longer than traditional gas cars or not. Yeah, and there's that too. Although I suspect that for most people, that's not really the number one priority. But still, if you're saving money and and they're kind of cool too, let's face it. But anyway, but yes, this is definitely a long-term trend. Yes, they're cool. They're kind of strange though, because they don't make the normal noises, do they? You can have one drive up right next to you and you never even notice it because they're so quiet. That's something that takes a little getting used to. But yes, those are absolutely a substitute. But remember, now you don't just go out and buy an electric car overnight. Like today you go to the gas station and the price doubled. You're not going to go out and buy an electric car tomorrow, but maybe in the next couple of years you might. And so that's why we do need to make a distinction between the short run and the long run. Okay, so, all right, let's just quickly run through these. The substitute goods, the closer the substitutes are, the greater will be the price elasticity of demand. Okay, so for example, if Coke suddenly becomes more expensive, people will switch to Pepsi or other sodas. So therefore, the elasticity is very high because of the very wide availability of very good substitutes. Gas, though, no. What else is there? Okay, in the short run, at least, you're going to have to just keep buying the gas because it's just, you have to get where you're going. In the long run, you might change your habits, but not in the short run. Now, the income, like I said, I think it's pretty self-explanatory. The more expensive something is, the more closely you'll pay attention to its price. That's just the way it is because it affects whether you can afford the product or not. All right. So the price of a newspaper, remember those ancient devices called newspapers? They were printed on paper. They still have them. If you go to any train station, there'll be a big stack of them for people who are getting on the train. But who cares if it's 50 cents or $1? It's a paper. You just buy it and you get on the train. But with a car, even a small percentage price increase could lead to a significant reduction in the demand for that car because it's a lot of money. Just like the computers and Starbucks example we had before. And then finally, with the time period, the longer the time frame we're looking at, the greater will be the price elasticity of demand for all goods because we have more time to find substitutes. And gas, to me, is the ultimate example of that, like we were talking about. If you have enough time to switch over to electric cars or just get a gas car that gets better mileage or move, the more time that goes by, the more you have time to switch and find replacements for gasoline. All right, So now we're not going to obviously have time to do this today, but we now want to look at the last two measures of elasticity. We're done with price elasticity of demand, but we have two others to consider, which are the income elasticity and the cross elasticity. But sadly, we'll have to save those for next week. Okay, we've run out of time. So we'll save those for next week, and you'll see that they're also quite interesting. And that's all I want to say now. So why don't we knock it off right here? And in the meantime, you should basically just make sure you're keeping up with the slides so you know what's coming up next. And at some point, I'll start giving you problem sets to work on so we can get some practice. But right now, let's hang on to that. And next week, we'll start up again right here with the income elasticity of demand. Okay. All right.
Thank
So
you.
I'll see you next time. Okay.
Thank you.
Bye. You too.